in space during cruise is the primary objective of RAD. So if we have the next graphic. The real question is, so why do we need to measure this on the surface of Mars? Well, the radiation environment on Mars is fundamentally different for two reasons. One is Mars doesn't have a global magnetic field protecting it from the charged particle radiation in space like the Earth does. Mars lost its magnetic field several billion years ago, and so it's pretty much bare and vulnerable to the deep space radiation which is present. Also, Mars doesn't have it has a much thinner atmosphere than Earth. It's about 1% the thickness of the Earth's atmosphere. So there isn't as much effective shielding or mass to absorb the particle radiation coming to it. So characterizing the radiation environment, measuring the radiation environment on the surface of Mars is essential for understanding the questions of habitability in terms of life-limiting elements of habitability, but also in planning for future human exploration. So if we could have the next slide. So this graphic shows two spacecraft. One on the left is the Mars Science Laboratory during cruise. It has the descent stage, the heat shield, the back shell, but it also looks curiously similar to the Orion spacecraft, which future astronauts will use to journey off into deep space to the asteroids and potentially Mars down the road. 20, 30 years. So measuring the radiation environment inside the spacecraft was something that we actually realized about a year ago. We weren't originally planning to take observations during cruise, and about a year ago we realized that this was a great opportunity because most of the time when you want to measure the radiation environment or the energetic particle environment, you put your detectors on the outside of the spacecraft to measure the pure interplanetary environment. But RAD is deep inside the spacecraft, in the belly of the spacecraft, basically as a future astronaut would be tucked in the belly of their spacecraft on a future mission to Mars. So we took these 7 months of data, and if you show the next graphic, this shows sort of a summary result of the particle flux that we observed during cruise phase. So it started on December 6th, 10 days after launch, and it went about 7 months and a week till July 13th when we finally turned off. And you can see two things in this plot. You can see this is a particle flux versus time, and you can see the galactic cosmic ray background, which varies slowly over an 11-year solar cycle. And then you can see these spikes. There's about 5 spikes on the graph, which show the results of solar energetic particle events as a result of solar flares or explosions on the sun, giant storms on the sun. And these came without a moment's notice. They happened very quickly. They lasted a few days, and then they were gone. But you can see that the particle flux that RAD observed, even deep inside the spacecraft, went up over an order of magnitude. So let's focus on one of the large events in March, if you show on the next slide. Just centering in on this region here in March. There were two storms, two events back to back. And if we have the next graphic, this shows a blow-up of this region. So the white data is the RAD observations, which, as I mentioned, they increased by about an order of magnitude in terms of the particle flux density. But the red is the pure deep space environment measured from the SIS instrument on the ACE satellite, which is pretty much along the line that the storm came from the sun. So the measurements that we see in red would be what RAD would experience, or what an astronaut would experience if they're on a spacewalk in deep space. And so the shielding or the protection from the spacecraft reduced the radiation environment by about 2 orders of magnitude. And that's essentially what we're going to learn from these cruise observations, in addition to comparing it with these other events that are observed from other spacecraft. But the lesson here is that these events happen very quickly, and they can be very intense. But with the proper shielding, we can help plan for and prepare for future missions to Mars. So I'll pass it on to Michael to talk about the cameras, which we'll be observing as we come through the atmosphere.
Thank you, Don. I'm here actually representing about 3 or 4 different teams. I'm the principal investigator of the mast cam, which are the science color cameras on the mast of the rover. I'm also here as the principal investigator of the descent imaging system, which will take pictures during the descent. Ken Edgett is the principal investigator of the Mars hand lens camera, which is MOLLE, it's called. Roger Weens is the PI of ChemCam, which is the laser that measures composition, but it also has a camera called the Remote microscopic imager, which will observe the actual location where the laser blasts. And finally, Justin Mackey, who is the lead for the engineering cameras, which are really the workhorse cameras on the spacecraft. There are 17 cameras on the spacecraft. And you might ask, why are there 17? The first graphic shows me 39 years ago, walking across a stream in Alaska, and it looks like I'm carrying someone. I'm actually, because my boots are around my neck, but the thing on my back is my 80-pound pack, and at the very top of that is a bag with 4 cameras. Geologists go in the field these days with lots of cameras, and the next graphic shows the rover, and it has lots of cameras that can be grouped into 3 different groups of cameras. On the mast, which you see at the upper left of the graphic there, are 7 cameras on the mast. Those are two pairs of navigation. Pairs because there are 2 sides of the rover computer, so each side can control one set of lenses, one set of cameras, and there are pairs of them because they're taking stereo data. So there are 2 pairs of navigation cameras. There's a single pair of mast cameras, but in fact they're really 2 different cameras. One is a sort of a 34 millimeter camera, which is very much like a 35 millimeter camera that you would normally have on your digital camera. The other is a 100 millimeter telephoto lens. And then the RMI is inside the ChemCam at the very top there. There is 1 camera on the turret, that's the Molly. That camera can get very, very close to the surface. It can resolve things when it's at its closest that are only a few tens of microns across. And then fixed to the body of the rover, and they can't move other than with the rover as it moves around, are the HazCams, the hazard cameras, which are used to look for where to put the robotic arm and also to look for hazards as the vehicle is driving. There are 2 pairs on the front and 2 pairs on the back. And finally, there's the descent camera, the MARTI, which is off on the side there. And one of the wheels will actually show up in the MARTI data. The next graphic shows, I think, is a video which we made of during a test where we show why we have so many different cameras. It's going to be a zooming in. This is a navigation camera, and it shows you sort of what we get with it. This is the 34 millimeter mast cam. This is now this is going to transition to the 100 millimeter mast cam, and finally with the view that Molly can get. And we'll zoom in on that as well. So the idea is that we can cover a range of resolutions from a few millimeters down to microns in scale. And the 100 millimeter mast cam at 1,000 meters distance has a 7.5 centimeter pixel, which means something about this big could be easily resolved about 0.6 of a mile away. The next graphic, now I'm going to switch gears and start talking about my baby, is the MARTI, the Mars Descent Imager. Give you an idea of the size. This is the same knife as you see in the picture. Geologists almost always use their pocket knife as a scale for small things. Normally, they also use rock hammers, but I didn't bring that with me. The MARTI is going to is a fixed camera, fixed focal length, fixed aperture. It takes images at about 4 frames per second. And they're color. They take color the same way your consumer camera takes color. It has a color filter on top of the detector, and that color filter is then used. We interpolate between the color filters to make a full full color image. As MARTI moves across the surface during descent, it will in fact take stereo images, mostly because the descent system is moving. The next slide shows how we're going to get the data back, or what's the pattern of it. You'll be hearing later today, I think, about the descent by the EDL itself. I had to learn a lot about EDL in order to be able to figure out how to get the images back. Because once we've taken them, they're stored, then we have to figure out what sequence to bring them back in. This graphic shows the basic phases of the descent and my attempt to bracket all the possible descents. The issue is really that the parachute descent takes longer than everything else, and it also can vary by a large amount. So the sky crane, which you'll hear a little bit more this morning, takes about 15 plus and minus 3 seconds. It's a very, very well-prescribed set of things that happens, and it's a very short interval. The power descent takes about 53 seconds plus and minus 3 seconds. So there's a very, very well-defined period of time when we know the vehicle is under power and when I could know which images would be coming back. However, the parachute descent could take anything from 45 seconds if the vehicle comes in low to 215 seconds if the vehicle comes in high. That is a huge uncertainty for me to know which pictures will have the most important information. So what I did is I took the absolute longest and absolute shortest time that was ever simulated by the EDL team, and those bracket the 1% probability at either end and also the middle. So these 5 bars here are those 5 cases of the 1% long or short and the 50% time and then the maximum minimum. And I said, okay, project, how many pictures can I get back? And we agreed that I'd get 18. So those white lines that you see there, numbered 1 through 18, are my attempt to divvy up all the pictures that I can bring back in the earliest phase of the mission. Those are images that will get something no matter what we land, so or how long it takes to land. So you can see that in the short duration, landing 109 seconds, only images through 7 are actually taken while the vehicle is above the ground, and everything from 7 to 18 are taken after the vehicle has landed. But then as you move out to the longer ones, you can see more images come back. And I spaced these so that I would ensure that we would get, at the very least, 3 images during parachute, 3 images during power descent, 1 image during sky crane, and potentially 1 image of the dust being raised as during the flyaway phase. And that's sort of why those are variously spaced and not equally spaced along the line. So the hope is that by pulling these back out of this long sequence, the sequence is 1,504 images in length, which is like 6 minutes and 25 seconds or more. That's how long we'll be taking the video during the descent. But most of that's going to be on the ground, and we'll be watching dust and other things in the sky. I think I have one last graphic. Yes. So in an attempt to lower your expectations, these are all going to be thumbnail. The thumbnails for the science cameras are bigger than they are for the engineering cameras. They're 192 by 144 pixels. So they're sort of YouTube sort of resolution, the poorer YouTube. And they're going to be in color. They are JPEG compressed for those of you who are knowledgeable about what your cameras do. Our cameras have a RAW form and a JPEG form, and the JPEG can be a different quality, just like you can set your consumer camera to a different quality. These will be coming back at quality very good, but not excellent. And so they're a little bit smaller, and small is good in terms of downlink. So they'll have artifacts, they'll be small, but we hope that we'll be able to actually tell where we land within the first few minutes of having them back on the ground. And with that, I'll turn it back to you.
All right, thank you, and thanks to all our panelists this morning. We're going to start the reporter Q&A session now, and we do have some reporters who are listening and watching from other locations, but we're going to start right here at JPL. If you do have a question, please raise your hand and wait for the mic to come to you. And when you do get the mic, please state your name and your affiliation. Okay, let's get a mic over here to row 3.
Yeah, this is.
Okay, we're just.
Yeah. My question's for John. Talking about the alluvial fan, this is entirely different from now. This is a very recent phenomenon from the recent past. Can you describe when you think in Mars history the alluvial fan was made, and presumably this is a drier time in Mars history, so how could there have even been significant water to take these sediments down the crater wall?
Eric, we only heard the last